Hello, physics students. Today we're going to look at the difference between centripetal and tangential acceleration. Now, consider this circus performer who is on a trapeze wire. In neither location does the performer have zero velocity. So the release point was somewhere up here. The performer is now swinging down. As she swings, of course, the velocity will be changing. As we move down, both the velocity is increasing as well as the angular velocity is increasing. Now, of course, these two variables are related. Now, just as a quick review, remember the relationship between the angular variables and the translational variables or linear variables, the ones that we worked with when we started the year with motion equations, is the velocity of the object will be equal to the radius of the motion times the angular velocity. The distance or arc length an object moves will be the radius times the angle. And the tangential acceleration will be equal to the radius times the angular acceleration. Now, omega must be in rads per second, radians per second. The angle theta, of course, is in radians. And the angular acceleration needs to be in radians per second squared. If that's true, then there's a simple relationship between all these variables. Now, the interesting thing about rotation is we are adding another acceleration on top of what we before called simply centripetal acceleration. Now, if you remember, centripetal acceleration always pointed to the center of the motion whenever an object was moving with a velocity v in a circular path. Now, in this particular case, at the beginning here, at this location, you have both centripetal acceleration and tangential acceleration. Whereas when she's at the bottom of the path, there is only centripetal acceleration. Now, to understand why, what we need to do is we need to apply the second law and look at a force diagram. So let's take a look. It is easiest to analyze the motion at the bottom of the path. Now, if I diagram the forces on this person here, there are two forces to be concerned with. We have her weight, which is pointing down, and we have the tension in the wire, which is pointing upwards. The center of rotation is above her. The length of the wire provides the radius of the motion. Now, if you look at the force diagram here, it is obvious that there is no force tangent to the path here. Since there is no force tangent to the path, there is no acceleration tangent to the path because you need a force to produce an acceleration. So if we, in this position, if we add up the forces, we can add up the forces and these will be equal to mass times the centripetal acceleration. So this is an easy equation to set up. That means that F tension minus mg will be equal to mac. And remember, the centripetal acceleration was equal to the velocity squared over the radius of the motion. We can also refer to this, if I remember also that v equals r times omega, we can recast the centripetal acceleration as r times omega squared. Now, so the acceleration here is again pointing to the center of the location in this direction. 1. Now let's examine the motion when she is higher up in the path. Now, the forces are not all aligned along the radial line now. If I diagram the forces now, I'll mark her center of mass. Of course, gravity still points down. And I called it weight in the other picture, so let's call it weight here. That's fine. And the tension points along the rope this way. Now, the tension is still pointing to the center of motion, so clearly there's a force, radial force, that's going to be causing a centripetal acceleration. But the weight now is not pointing along the radius line. It is also not truly tangent. So I would have to break the weight up into two vectors. I have this tangent portion of the weight, and I have this portion of the weight perpendicular to it. Now, by geometry, this is going to be the same angle as the angle on the string. Now, in this case, this force, by a little bit of trigonometry, you see that the tangent portion of gravity here is actually mg sine theta, and this perpendicular portion here would be mg cosine theta. It is this tangent part of the force that makes a tangent acceleration. So in this case, I would need two force equations. I would have the tension. I would have tension minus mg cosine theta. That would be equal to MAC. And in the tangent direction, I would simply have mg sine theta equal to mass times the tangent acceleration. So there are two accelerations. There are actually the same pieces of one acceleration. So this tangent and the centripetal acceleration basically act as components of the acceleration vector. So if we make a quick little sketch here, so now there are two accelerations present. We have a centripetal acceleration in this direction, and we have the tangential acceleration in this direction. Now, if you know the angular acceleration, you don't need to work with the force equations. The homework problem that I gave you, the angular acceleration was given. So this tangential acceleration will simply be r times alpha. The centripetal acceleration will be equal to v squared over r, or if I put it using the motion variables, r times omega squared. But the true acceleration is if I add these two vectors tip to tail. Now, if they are even in size, the true acceleration would point in this direction. So something like this. This is actually the net acceleration, which would be the vector sum of the centripetal and the tangential. I hope this helped explain things. So again, you could solve this problem with forces if we needed to. But in this case, since I had the angular velocity and the angular acceleration, it was not needed. And again, if I want to find out what this angle would be here, well, then the AC would be over here. This would be AC. And I see it's going to be, this angle to be an inverse tangent of AC over AT. So I hope this helps, and I'll see you in the next video.